Thanks for inviting me. I'm very, very happy to be able to give this talk. So I'd like to tell you a little bit about my work on voting theory with Wes Holliday at Berkeley. So most of this work is joint with Wes. And of course, as a logician, I'm always worried about giving talks that don't have a lot of logic in it. But this talk actually does, even though it's really on social choice theory and voting theory, the way Wes and I approach this field is very much from a logician's point of view. And we will be talking about lots of maximizations, although there's no sort of formal logic involved. Although in at least one of our proofs, we do use computational logic to prove our result, and I'll try to point that out. Okay, so let me just introduce the voting problem. So the voting problem is you have a group of agents, which I'll typically call voters, and there's a set of alternatives, which I'll usually call candidates or maybe just an alternative. And the question is, how do these group of voters choose an alternative from this set of candidates? Now, each voter is asked to select a ballot that is intended to express their preferences about the alternatives. And so the question is, how should we fairly pick an alternative from X that's based on these submitted ballots? Now, allowing for ties, so allowing for the fact that we might in some cases have to say that two candidates or two alternatives are tied, we're really talking about picking a subset from the set of candidates X. And then the idea is perhaps some further random mechanism will eventually pick the final single alternative from that subset. Now, I have a Stanford Encyclopedia article in which I survey a lot of different methods, a lot of different algorithms you might use that, given the ballots from the voters, decides on which subset of the alternatives are declared the winners. And Wes and I have also been putting together an open source Python package that allows you to run lots of different voting methods and compare and contrast them and so on. And in some of our other work, we take a very computational or quantitative point of view to answering some of these questions. So if some of these issues arise, some more quantitative issues, I have studied this in detail, although that's not what this talk is about. Okay, now in general, there are lots of different types of ballots that you might require voters to submit. So on the one hand, you might have rankings. So this is an actual example of a ballot from San Francisco, where voters were given a set of candidates and they're asked to decide who is their first choice, second choice, third, fourth, and so on. So that's submitting a ranking over the alternatives. Other types of ballots are asking you to do more things like grading the candidates. So you assign which candidates you approve of, or even assigning an actual score to those candidates. Now, in this talk, I'm going to focus solely on rankings, and most of our work is focused primarily on voters submitting rankings of the candidates. I have a bit more to say about whether or not one should use grades or rankings, but I'm going to kind of set those issues aside. So now, essentially what we're working with are ordinal preferences. So if we have an election for a set of candidates X, the idea is that each voter from a set V of voters has an ordinal preference between the candidates. For any pair of candidates, we will have that I prefers A to B, or I prefers B to A, or I simply doesn't have a strict preference between them. And here we're a little bit silent on what exactly does that mean. Does that mean you're indifferent between A and B, or you can't compare A and B or whatnot? So generally here we're, at least for this part of for this talk, I'm going to assume that voters have a linear ordering over the candidates. So for every pair of candidates, either you strictly prefer one to the other, and that's pretty much the only opinion that you can have. So a preference profile P is what we're really calling an election, but a preference profile assigns to every voter a ballot which tells us whether or not, so if AB, the pair AB is in P of I, that means voter I strictly prefers A to B. If BA is in there, that means I strictly prefers B to A, and so on. And we're going to kind of rule out this last case just for simplicity in this talk, although I have more to say about this, the case of indifference and incomparability later on. Okay, so now given a preference profile P for a set of candidates a set of candidates X and a set of voters V, the question is, how do we decide who wins the election? So the voters have submitted their ordinal preferences over the candidates X, and the question is, how do we decide who actually wins this election? Now, when there's two candidates, there's a traditional answer to this question, which is just simply majority voting. So if more voters prefer X to Y, then X wins. And if the same number of voters prefer X to Y as Y to X, then there's a tie. Now, this is a very intuitive answer, but what social choice theorists are really interested in is the question, why should we use majority voting? And this is really a big topic, and there's a lot that one can say, and this gets into topics in political philosophy and the theory of democracy and so on. But we're going to take an axiomatic approach. So let's look at one argument, a very famous argument from Kenneth May. So there's a theorem called May's theorem, and it's easy to state. It's actually not a very difficult theorem to prove either. But imagine that we have a function that inputs a preference profile for V, where we have just two voters, let's call the voters A and B, and always outputs a non-empty subset of A and B. So May's theorem, essentially what you're doing is you're considering all such functions, any such function whatsoever, and we want to write down a set of normative principles or a set of axioms that uniquely picks out majority rule. So May's axioms are very natural. So the two key axioms are anonymity and neutrality. So anonymity basically means the names of the voters doesn't matter. So if voters swap ballots, then this doesn't change who wins according to F. And neutrality says if the positions of X and Y switch in every voter's ballot, then X is a winner according to F before the switch, if and only if Y is a winner according to F after the switch. So this ensures anonymity ensures fairness for the voters, and neutrality ensures fairness for the candidates. Then May has a key axiom, which he calls weak positive responsive. Well, he actually calls it positive responsiveness, and Wes and I noted that you can actually weaken it. So this technically is a slightly different principle, but the difference doesn't really matter for us now. And this is kind of a monotonicity principle. It says, for any two profiles P and P prime, suppose one that A is in F of P. So if A is in F of P, that means either A wins or A is tied in P according to F. So A is a winner, but it might be a tied winner. But now let's consider P prime. Now, P prime is obtained from P by taking one voter that had A ranked uniquely last. So for example, that voter had the ranking B above A, and this voter changed to the ranking A above B. So one voter, and only one voter, moved A from the bottom to the top of their ranking. If that happens, then in this new profile, A must be the unique winner. So this is a monotonicity principle because it basically says more support is always better for you. More support can only help you. Now, this theorem says that, May's theorem says that if you take any function that inputs any profile for V and a pair of candidates A and B, and output a non-empty subset of A and B, then the following are equivalent. F satisfies anonymity, neutrality, and weak positive responsiveness, and 2, F is majority voting. So this gives a justification for majority voting just by pointing to these normative principles of group decision making, and basically says, look, if you want, when you have two candidates, if you want these normative principles, then you have to be using majority voting. Any other way of deciding the winner will violate at least one of these principles. So this provides and you can think of this as providing an axiomatization of majority voting. Okay. Now, so in the case of two cases, you can basically say the problem of voting is solved for two alternatives. But when you move beyond two alternatives, that's where we get into interesting paradoxical situations. And a lot of you probably have heard of this paradox. So consider this election in which we have 3 n voters, where n is any number. Okay. And we have the voters that rank these three candidates in the following way. So this means N people rank A above B above C, N people rank B above C above A, and so on. So now, if we start asking what are the head-to-head comparisons, because after all, we know when there's two alternatives, we should use majority rule. We can see that when we compare A versus B, that two N voters prefer A to B, while N voters prefer B to A. So we can say that A beats B by a margin of N. And I'll draw that by drawing a graph from A pointing to B labeled by the number N. We also see that B is majority prefer, or B beats C, because two N voters prefer B to C, while N voters prefer C to B. So B beats C by a margin of N. And now here's where the paradox comes in. You might say, well, if A beats B and B beats C, well, of course, A beats C by transitivity, but this notion of beats violates transitivity. And if you just look, you see that C, in fact, beats A by a margin of N. So the problem here is that if we apply majority rule to every pair of candidates, we get that every candidate is defeated, so no one actually wins this election. And this is often known as Condorcet's paradox, and it was discovered in the late 1800s. Now, so one question voting theorists have been struggling with is, what do we do in these types of situations? Now, this paradox was actually rediscovered in the 1940s by Ken Arrow. And what Arrow was interested in is not really a voting method, but something a little bit more sophisticated than a voting method, which I will call a collective choice rule. So a collective choice rule is going to be a function f that inputs a preference profile p, but outputs, rather than a set of winners, it outputs actually a binary relation on on the set of winners, on the set of candidates, where we're going to take AB as an element of FP to mean that A defeats B in P according to F. And this is what I was trying to use majority rule, the question of when does one candidate, like if a candidate is majority preferred to another candidate, as a notion of defeat in for a profile. And then the idea is that the winner is going to be any of the undefeated candidates. Any candidate that's not defeated in the election is going to be the winner. Now, we've seen that majority voting can, in fact, judge that every candidate is defeated. So Arrow then asked the question, can we find any collective choice rule that satisfies a desirable set of axioms? Now, I don't want to dwell too much on Arrow's theorem. I just want to point out one sort of key axiom that I'm going to refer to later on. But he starts with three principles that are actually very, very hard to argue with, although social rationality, you might argue, can be denied. But so universal domain just says that every profile is in the domain of the CCR that we're trying to axiomatize. Social rationality says the output should give you some type of ranking over the candidates, possibly allowing ties, and there's a question whether or not it ought to be transitive or not. Pareto, this is a very normative principle. It says that if all voters prefer X to Y, then X must defeat Y according to your CCRF. Now, Arrow's key principle is what's known as independence of irrelevant alternatives. And what it says is that the social ranking of X versus Y depends only on how the voters rank X and Y, and not how they rank other alternatives. Okay, and so the basic idea is that if we take two profiles, P and P prime, and we restrict attention to how they rank X and Y, so this P restricted to X and Y just says, look at all the voters and ask, how do those voters rank X and Y? And that's all we actually care about. If those restrictions are the same, then society's opinion about whether or not X defeats Y has to be the same under P and under P prime. So independence of irrelevant alternatives, it's a very natural principle, because after all, the relative comparison of X and Y should depend only on the voters' opinions about X and Y and not on other irrelevant facts about the election. Now, Arrow proved, this is a very famous result, that if there are at least 3 alternatives, and by the way, the number of voters has to be finite, that's also a crucial assumption here, then the only CCRs that satisfy universal domain, social rationality, Pareto, and independence of irrelevant alternatives is something that does not satisfy anonymity. And in fact, it violates anonymity in a very, very strong way, in the sense that the CCR must be what Arrow called a dictatorship. And a dictatorship just simply means that there exists a voter such that for all profiles P and all candidates X and Y, if I prefers X to Y, then society must prefer X to Y. Okay, and it's really important to get the order of quantifiers here. There is a voter such that for all profiles P, if the voter prefers X to Y, then society does. If we had the other way around for all profiles, there is a voter such that if that voter prefers X to Y, then X defeats Y according to F and P. That, of course, is no big deal. That's satisfied by just about every single CCR. All right, so Arrow has this sort of deep, it's often interpreted as a deep impossibility theorem because we can't find any CCR, any way of making our group decisions that satisfy these normative principles. All right, now you might say, well, hold on a second, let's just pause here for a second and think about what's going on. We're drawing this very, very negative conclusion, this impossibility result, from this profile right here. And you might say, well, why would we expect there to be a single winner in this case? Isn't the answer very simple? Look, this profile is perfectly symmetrical. I mean, if you try to find a way of breaking a symmetry between A and B, you'll see it fails. Like, everybody's ranked first by N people, everybody's ranked second by N people, everybody's ranked third by N people. There's really perfect symmetry between A, B, and C. And so obviously the right answer in this context is that all the voters should be, all the candidates should be tied for the win. And indeed, in the analog in the 2-candidate case is really where one voter ranks A above B and another voter ranks B above A. The only sensible decision in that case is that A and B are actually tied. So, and you can even prove that anonymity and neutrality, they imply that in this profile, you have to select A, B, and C as all being undefeated and being tied for the win. Now, from this point of view, you might say, look, the possibility of a perfect tie does not seem to be a fatal to the theory of democracy. And in fact, the probability of seeing a perfectly symmetrical profile like this, that's going to go to 0 as the number of voters increases. Okay, so what instead we should be thinking about when we think about these types of majority cycles are elections like this. And this is an actual election. This is a simplification of a majority cycle from a 2021 Minneapolis City Council election, where we had, I think there were more candidates, but we restricted attention to just the top 3 candidates here. And in the top 3 candidates, there was a majority cycle. So R is majority preferred to Y, Y is majority preferred to C, and C is majority preferred to R. So there is a cycle, and according to majority voting, every candidate is defeated. So there is no winner if you just focus on majority voting. But I want to claim that it's perfectly clear in this context who the winner should be in this election, namely Y. Candidate Y should jump out at you as the obvious winner in this election. And there's really 2 reasons why I should jump out of you, namely I loses by the smallest amount, but of course I also wins by the biggest amount. Okay, and you might say, well, look, so which do we focus on? How much does a candidate lose by, or how much does a candidate win by? For various reasons, at least in this talk, we're going to be focusing on trying to minimize the loss. That's what we're going to focus on. And if you have questions in the question period, I can say more about why we focus on minimizing the loss. I mean, this will come out in that this gives us very natural normative principles if you focus on minimizing the loss rather than maximizing your win. So if we generalize this idea, so what idea am I talking about? The idea is that if there's a cycle, then what we're going to do is we're going to identify the winner that has the smallest loss. That's what we're going to do. So in this cycle right here, we look at the incoming edges and we see which incoming edges has the smallest margin. And we're going to, the one way to think about it is we're going to remove that edge and say that's not really a defeat because in this context, the voters are a bit incoherent. So we have to raise the threshold of what it means to say that one candidate defeats another. It's not just that you have a simple majority, but rather you have to beat somebody by more than 22. So that's the idea. And if we generalize that idea, we get a voting method. And really what this is a voting method, and also it gives you a defeat relation that Wes and I called split cycle. And the idea of split cycle is actually very, very simple. So what we do is we look at an election, we look at the margin graph of that election, and then you identify all of the majority cycles in the election, if there are any. Now, in every majority cycle, what you want to do is you want to identify the head-to-head win, the edge in that cycle, with the smallest margin of victory in that cycle. Now, after we do that for all the cycles, sort of in parallel, think about it happening all in parallel, we discard all of those identified wins, and anything that remains counts as a defeat of the losing candidates. So let me give an example because this will illustrate what's happening. And things can get more complicated when you have more than 3 candidates. When you have 3 candidates, there's only sort of 2 cycles. They go in opposite directions, and that's basically all you have. But already with 4 candidates, we can see quite a lot of a bit more sophisticated types of margin graphs. So suppose you have an election that generates this margin graph. The first thing we need to do is identify all of the cycles. So a lot of you probably have noticed that there's 2 cycles, but in fact, there are 3 cycles in this margin graph. So we have this little red cycle here, this blue cycle, and then we kind of have a zigzaggy cycle, this green cycle. Okay, so that's the first step, identify all of the cycles. The second step is you identify the smallest margin in each cycle. So this is in the red cycle, it's the A to D edge. In the blue cycle, it's the C to B edge. And in the green cycle, it's the C to D edge. These edges can't be defeats. That's the idea. We got to scratch those edges off of the margin graphs. All other edges that remain that haven't been scratched off by one of the cycles, those are going to be considered defeats. So we end up with a little defeat relation here where D defeats B, B defeats A, and A defeats C. The candidate that is undefeated is going to be the split cycle winner. So in this context, D is undefeated, so D is going to be the split cycle winner. So one thing I'll just go ahead and point out right now, the notion of split cycle defeat, and this is really crucial, is not going to be transitive. So D defeats B, B defeats A, but it's just not the case that D defeats A. And that's actually, I mean, that's really crucial. You really need to drop transitivity in your notion of defeat to get around Arrow's theorem. That's one general thing to note. Okay, so that's a natural, simple algorithm. Things aren't too complicated there, but there's a good question. Why should we resolve cycles in this way? I mean, all of us could probably think of other algorithms that one could follow that would resolve majority cycles. There are a variety of ways in the literature in which one might resolve majority cycles. So why do we think that this is a good way to resolve majority cycles? So what makes split cycle special is that it responds to the inclusion of new candidates and new voters in a reasonable way. So in particular, split cycle satisfies the following two normative principles. So one is called immunity to spoilers, and the other is called positive involvement. So let me explain what these principles say. So immunity to spoilers is about the addition of new candidates. So it's really about the addition of a new candidate B. So imagine you have an election P, and then you consider what happens in the election without B in the race. And what you note is that A wins without B in the race. And moreover, A is majority preferred to B. So more voters prefer A to B. Then immunity to spoilers says it can't be the case that both A and B lose in the election P. Okay, so it rules out a particular type of spoiler candidate. I'll come back to what positive involvement is in just a second. So let's say that a candidate B is a spoiler for candidate A, provided that A would win without B in the election, A would beat B in a head-to-head election, but neither A nor B wins in the election. So here's the picture. Suppose we have an election with these four candidates, and we see that the green candidate wins. But then if we restrict attention, and so what I mean by restricting attention is we just, in everybody's ballot, we scratch off their ranking for this purple, this last candidate right there. We scratch off in everybody's ballot, and we see who would win in that case. So it's not a different election in the sense that the voters are allowed to submit different rankings. It's rather we have an election and then we scratch off. It's as if the purple candidate said, I'm sorry, I'm no longer available to run. Maybe I'm in jail or something like that. So I'm no longer able to run. And so therefore we ask, okay, now after gathering all the ballots, who would win the election? Now, by itself, this is no big deal. This means, A wins in the sub-election, but in the bigger election, a different candidate wins. And, this might have to do with the fact that a lot of voters prefer this last purple candidate to the first red candidate. So red actually looks like a defeated candidate with the purple candidate in the election. However, we want to say that the purple candidate is a spoiler for the red candidate, for this red candidate, if in addition to A winning in the sub-election, A actually wins in a different sub-election, namely in a head-to-head comparison. So that just simply means that A is majority preferred to the purple candidate. So in this type of election, if in this type of setting, we would call the purple candidate a spoiler for the red candidate. And in fact, in actual elections, we've seen examples of spoilers. So the most famous example is the 2000 presidential election in the US, where Al Gore would have won in the election had Nader not been included. Plausibly, Gore would have beat Nader head to head, but with Nader in the election, another candidate, namely Bush, won the election. There's another voting method called instant runoff or ranked choice voting, and you get similar types of examples. The most recent is in 2022. The candidate, a Republican, Nick Begich, would have won the election had it not included Palin. A majority of voters preferred Begich to Palin, and yet with Palin in the election, not only did Nick Begich lose, but also Palin lost, and this other Democrat, Mary Patola, ended up winning the election. So immunity to spoilers is a principle that rules out this type of phenomenon. That's the idea of immunity to spoilers. Okay, so that's immunity to spoilers. So that means if your voting method satisfies immunity to spoilers, it responds to the addition of new candidates in a reasonable way. Now, another principle is positive involvement. So positive involvement says that if A would win in P and P prime's obtained from P by adding one new voter who ranks A uniquely in first place, then A still wins in P prime. So here's a violation of positive involvement. We have an election, don't worry about the details of the election, but we see that C is the unique winner. We add one voter to the election in which C is ranked uniquely on top. And in that case, somebody else turns out to be the winner, namely E. So this is sort of an absurd principle if you violate positive involvement, because it basically means you're a winner. You gain more support by getting more voters to come in and vote for you, ranking you uniquely in first place. And then you end up not winning the election. So immunity to spoilers and positive involvement, these are both properties that move us to what's called a variable election setting. So the profiles have different sets of candidates and different sets of voters. So it's a more general setting than what Arrow was working in. But of course, this is what happens in actual elections. Okay. Now, Wes and I have our first theorem about split cycle is that if you take all the axioms from May's theorem and you add to it immunity to spoilers and positive involvement, then you essentially uniquely pick out split cycle when we restrict to just 3 candidate elections. Now, that's not exactly correct. We do need 2 additional axioms. But those axioms are very, very minimal. So for example, one is called homogeneity. If A wins in an election and then you clone every voter, so you just multiply every voter by 2, then A should still win in that election. And another sort of general principle is that if A wins and you move to a new election in which exactly 1 voter submits each linear order of the candidates, so that's like a giant block where everything's tied, then A should still win in P prime. So essentially, taking May's axioms together with immunity to spoilers and positive involvement gives us split cycle when we're in 3 candidate elections. Okay, so that's a very nice result. That just shows the natural extension of May is to go to split cycle if you want to satisfy immunity to spoilers and positive involvement. Now, to axiomatize split cycle for more than 3 candidates, we have to return to Arrow. Now, Arrow said, let's return to this IIA axiom, independence of irrelevant alternative. Arrow says that if X defeats Y in a profile P, and P prime is exactly like P with respect to how every voter ranks X versus Y, should it follow that X defeats Y in P prime? So Arrow's IIA axiom says yes, it should. That should follow. That should be that follows from the axiom. But Wes and I are going to say, well, no, not so fast. P prime might be sufficiently incoherent that we might actually need to suspend judgment on many defeat relations that could be coherently accepted in P. So let me give an example here to illustrate my point. Consider this election right here. Now notice in this election, the relative rankings of A and B is enough to be sufficient for A to defeat B. Because if you notice, 2 N voters rank A over B, and only N voters rank B over A. So A is actually majority preferred to B in this case. Okay? And we want to argue that in this profile, in fact, most voting methods are all going to agree that this is this margin of victory in this profile is sufficient for A to defeat B. But now, if we go to a different profile P prime, and the rankings of A and B are identical, the rankings of A and B haven't changed. The only thing that has changed is where people have placed candidate C. Then we're back into the original Condorcet paradox profile. And in this case, anonymity, neutrality, and a general principle of availability, which just says somebody must be undefeated. They all say that no such CCR can say that A defeats B. So we think of this as a counterexample to IIA as a normative principle that sort of recommends which candidates ought to be defeated in a particular election. So our idea is that we have to move away from the local evaluation of X versus Y, but you do that only when increasing incoherence demands that you're more conservative in locking in defeat relations. So we propose a weakening of IIA called coherent IIA that says if X defeats Y in P, and you go to another profile in which the rankings of X and Y are identical. So this is just like IIA, the IIA principle. Now, IIA is going to say that X must defeat Y in P prime. What we say is we add this extra condition that says, look, the margin graph of P prime must be obtained from P by deleting 0 or more candidates other than X and Y, and deleting or reducing the margins of 0 or more edges not connecting X and Y. Okay, so basically the idea, and then in this case, X should still defeat Y in P prime. So the key idea is that the operations in 2 that cannot increase the cyclic incoherence with respect to X and Y. You can't sort of add cycles and involving X and Y. So coherent IIA is a weakening of IIA, and it turns out to be a key principle in axiomatizing split cycle. So let me just check the time. Okay, so I'll manage my time a little bit. I'll try to wrap up fairly soon here. In one paper, Wes and I showed that split cycle is the most resolute CCR. That is, it locks in all the defeats of any CCR, satisfying coherent IIA and the following 5 axioms. Now, anonymity and neutrality, that's from May's theorem. Availability says there's always some undefeated candidate. Homogeneity is exactly what I said before. If A defeats B in P, then it still defeats B in 2P, where you clone all of the voters. Monotonicity is kind of a weakening of the positive involvement axiom. And then one key axiom that's sort of less obvious might be neutral reversal. That just says if you take P and you add exactly 2 voters that have reversed linear orders of each other, then the defeat relation can't be different in P than it is in P prime. So this is sort of half of an axiomatization of split cycle, because it says that any CCR that satisfies these principles here, including coherent IIA, must refine split cycle. We got a complete axiomatization with Yifeng Ding, in which we added 2 additional axioms, namely coherent defeat and some version of positive involvement. So any CCR satisfying the following axioms locks in all the defeats of split cycle. So it matches exactly split cycle. So coherent defeat says if more voters prefer A to B than vice versa, and there just are no majority cycles involving A and B, then A must in fact defeat B. Okay, so split cycle is the unique CCR satisfying all of the above axioms that I've said on the previous 2 slides, and coherent IIA. Okay, so this gives us a complete axiomatization of split cycle, which is very nice. However, there's a problem, and I don't have much time to dive into the details of this problem, but let me just give you a sense of what the problem is. There's a problem of ties. Now, as I mentioned before, there are certain profiles, perfectly symmetrical profiles, in which no anonymous and neutral voting method can pick a unique winner. However, split cycle will not pick a unique winner when things are sort of completely asymmetrical. So if you look in this margin graph, all of the margins are completely different. So all of the margins are different. There's no symmetries at all involved here. And in fact, yeah, you can make this very, very extreme, where you just don't have any symmetries between any of the candidates. Yet still in this case, split cycle will identify B and D as being tied for the win. Now, you might view this as a problem for split cycle because it's just not being very resolute or not resolving who the winner ought to be in a deterministic fashion. So let's say that a voting method is resolute if it selects a unique winner in every profile. Now, that's, of course, inconsistent with anonymity and neutrality. But I'm going to skip over asymptotically resolvable. But let's say that a voting method is quasi-resolute or quasi-resolvable if there's a unique winner in any profile that's uniquely weighted. That is, in a profile that generates a margin graph that looks like this, where there's no symmetries between any of the candidates. So let me skip over that point. Now, in some context, it might be acceptable to choose uniformly at random from among the split cycle winners to break a tie. However, if you only want to resort to random tie breaking in very, very exceptional cases, then the question is, how should you decide who the winner is? Now, in this is the profile in which split cycle picks two winners, namely B and D. If you look at other voting methods that exist in the literature, you have beat path and you have ranked pairs and so on, and other types of voting methods. The details don't matter. I can go through the details in the question period. We see that beat path and ranked pairs happen to refine split cycle in this setting. Minimax does too, but that's actually just an accident in this example. Beat path and ranked pairs are both quasi-resolute, and they're always guaranteed to pick a refinement of split cycle, to pick at least one of the winners from split cycle. And they're quasi-resolute. In uniquely weighted margin graphs, they always pick a unique winner. So one problem, so you might say, okay, great. Well, let's pick between beat path and ranked pairs. Let's use those instead because they're always picking a split cycle winner, but they always pick a split cycle winner, but they're more resolute in uniquely weighted margin graphs. The problem is beat path and ranked pairs both violate immunity to spoilers. So in order to be more resolvable, you have to give up our nice principle of how to respond well to the addition of new candidates. Okay, and in fact, they violate a stronger principle, which is called stability for winners. But in the interest of time, I don't want to spend time talking about going through the details of that. But let me just mention one sort of axiom, which you might say, well, look, okay, fine. Beat path and ranked pairs are quasi-resolute. They refine split cycle, but they don't satisfy immunity to spoilers or the stronger axiom stability for winners. So let's go out and find one. Well, that turns out to be impossible. So actually, this result used SAT solving to prove our result, plus some other, I can go through details of how we proved that. There's no voting method that satisfies anonymity, neutrality, stability for winners, which is the strengthening of immunity to spoilers, and quasi-resoluteness. Okay, so this leaves us with the question as to how do you resolve ties in split cycle in a deterministic fashion. We did propose a way of refining split cycle, but I think in the interest of time, I'm not going to be able to say much about it, called stable voting. But if you have questions in the question period, maybe we can talk about that. So I have a few slides on stable voting, but let me just go ahead and go to the concluding remarks. So we wanted a voting method that resolves well to the addition of new candidates to the election, and we wanted it to respond well to the addition of new voters to the election. And that voting method is split cycle, so you can prove it. It satisfies immunity to spoilers. It also satisfies positive involvement. The problem is split cycle is not resolvable. There are cases in which we think split cycle ought to deterministically pick a single winner, but it doesn't pick a single winner in those cases. So now the question is, I would like a voting method that's resolvable and say responds well to the addition of new candidates. Well, that turns out to be this other voting method that Wes and I proposed called stable voting. And we also found a voting method that responds well in the sense that satisfies positive involvement and is resolvable called minimax. But there's a big question here for us. Is there one that satisfies all of these three principles? And as of right now, we don't know of a voting method, but we do very strongly believe either we're going to be able to prove it's impossible, or we will be able to discover such a method. All right, so split cycle provides a resolution to the problem of majority cycles discovered by Condorcet. We provided a complete characterization by compelling axioms. We actually have implemented split cycle, so we use it at a website called stablevoting.org, in which you can run polls, and it actually uses split cycle and stable voting to break ties. There's lots of additional topics that I didn't have time to cover, in particular talking about stable voting. So if you'd like me to say more about that, I'd be happy to in the discussion period. But what happens if voters are allowed to submit ties or truncated ballots? There are other ways that you might compare voting methods, not just in terms of their axioms. You might want to study elections in which voters may strategize. Or broaden the types of ballots, so we consider grading system or more general probabilistic voting methods. I'm actually involved with a group, Wes and I are both involved with a group that's trying to get some version of essentially a refinement of split cycle to be used in US elections. So I think I should leave a bit of time for questions. So I should just say thank you very much. And if you'd like me to go into more details about anything, I'm happy to address your questions. So thank you very much.